Okay, hello everyone and welcome. My name is Lesia, and I'm right now assistant professor at Rutgers University, Computer Science Department. And this is my colleague Judy, and she's from University of North Carolina at Chapel Hill. And today we are very happy to talk to you about our tutorial, which is titled From Underspecification to Alignment, Breaking One Model Mindset for Trustworthy AI. And as you might have guessed from this title, we both work in trustworthy and reliable AI. And when you think about it, so the goal is to make systems that not only perform well, but also that, well, we can rely on, right? That are safe to use, that we can understand, that we can trust. At least it would be really nice to have that, especially if you go in like high stakes domains that influence our human lives. And then when we talk about alignment, we often mean aligning with human values. So huge teams of researchers right now and engineers are working hard to make this model, for example, less harmful, or for example, by filtering some toxic comment, and also have to make them less biased according to like what they encountered online. So basically, they're building almost like behavioral safeguards in order to ensure that the systems are nice to use. But as you think about alignment, there is another, maybe deeper level to it, which is user intent. And compared to like thinking about toxic comments, it's like a little bit far less understood. So what does it mean, user intent? Who is the user? Who is that stakeholder? What are their goals? What they care about? What they want to look at? So there are so many different questions that make that problem a little bit more complex. And also, depending on that stakeholder, depending on which level they are, let's say, let's compare a developer and then the user of our system, they may have completely different point of views on whatever they want to use the systems. So they may require they may have different requirements to the systems as well, which leads to this fact that very often, given the same problem, given the same question and the same goal, there could be multiple different passes depending on the stakeholder and multiple different answers to the same questions. So basically, I'm trying to say that very often there is no single golden answer, and instead multiple different ways that we can take and we can go and we can answer our questions. And this multiplicity, or we call it Rashomon effect. And during this tutorial, this would be a point of our study. So we're going to try to define it, understand where it comes from, why it occurs, how we can use it. But basically, on a higher level, it occurs when we have many different perspectives on the same problem. So for example, as in this image, there is clearly different viewpoints, and both of them are correct, but they are very distinct, describing the same phenomena or the same date. So during this tutorial, we're going to go through a few steps. First, we're going to introduce that Rashomon effect a little bit informally. We're going to look at some examples when it occurs. We're going to look at some from like language to vision to tabular data sets. And then we're going to try to understand why it could occur. What could be the reason for that? Then we're going to try to characterize it, meaning is there a way to measure it or to understand it or somehow deal with it? And during this process, we'll have a small hands-on activity just for you also to interact with like different models. And then finally, we conclude with implications to trustworthy AI. So if you think about having multiple different models, so many pathways from start to goal, then maybe there are different applications into like our fairness, interpretability, explainability, feature importance, and other important things that we can think about that we care about in machine learning. And we'll conclude with future directions and open problems that we are excited to work about, and hopefully we can get you interested to work on as well. Okay, so let's then get started. And I would like to give you an example, almost like a little fairy tale of my own research. And maybe it will resonate a little bit with your own experiences as working especially with like domain experts or working with somebody who has some domain knowledge where you try to apply machine learning algorithms. And in this case, I will use a medical example about detecting epilepsy. And it influences around 50 million people worldwide. So it's like an important problem to try and understand where the seizures occur and what are the spikes in the seizures, can we detect them reliably? So in order to tackle this problem, we were provided with the data, which is actually quite good data. So we had like EEG signals, which are different dimensions, and our goal was to detect a spike. And we were given probabilities from domain experts. So we have this good quality data, we have very clear goal, we are very clear to use really good neural network model for that well-defined problem. But because we have doctors on our team, we have domain experts, so we wanted to do something a little bit better and said, okay, let us try to do interpretable neural network model. So we use prototype neural nets, and I will not cover them today, but if you're interested, I'm happy to chat about that offline. And we have a baseline, which was a neural net, black box neural net, which was around 85% accurate. So we tried out of box our prototype neural net, and we also get 85% accurate model. And we are so happy. We like had this better explainable system that tells how it makes its decision, explains us what it's doing. And we come to our doctors and say, hey, we got this great model. And they look at it and say, I don't get what it's doing, like at all. It doesn't correspond to like my feeling of what I know about this medical data. We're like, okay, can you please educate us and teach us about how do you make these predictions? So we get some information, we go and try again. They say it doesn't correspond to my medical intuition again. And we went through this process maybe like 10 times. Interesting part, all of these models have been around 85% accurate. All of them met a bad baseline, but only towards our interaction, we finally were able to converge to a model that they said, okay, now I'm happy with it. It aligns with my expertise. Furthermore, our user study also showed that it aligns with expertise of other doctors who work in this area. So let's for a second think procedurally what happened during this process. And let me consider like hypothesis space, which would be like my different neural network models, and it will be represented by this yellow blob. And remember I said we had this black box baseline, so this would be my blue model somewhere in this yellow blob. And now, as I go through all of these iterations that we were mapping to, they were all approximately the same accurate. So you all map to this area in my hypothesis space of near optimal models. And we will call this that Rashomon set, basically that near optimality where you have multiple models with different properties, but they all perform approximately equally well. And why do I call this Rashomon? There is an interesting movie from 1950 from Akira Kurosawa, and it's called Rashomon. And it revolved around four characters. They relived the same tragic event and then later asked in court, oh, what happened? And they gave very different and even contradictory statements. So then this term found its way into journalism, and finally in 2001, Leo Brayman was like playing with linear regression. And he noticed that very often for the same data set, you can get different linear models that have different coefficients, but the same error rate. So essentially he said, what I call Rashomon effect is that there is often multitude of different descriptions in a class of functions given approximately the same minimum error rate. And this is like a paper called Two Cultures, and it's like a very inspirational paper at that point, which I think still has a lot of implication into modern machine learning and AI systems today. And while I prefer term Rashomon effect because I believe it captures a little bit wider phenomena, this kind of like uncertainty, if you think about it, model uncertainty, has also been known in literature under different names. So we'll think about Rashomon effect as having many distinct models within the same performance, but also it has been known as underspecification. And if you would like to do some causality here, which may be a little bit of a stretch, but essentially underspecification is one of the reasons of the Rashomon effect. By underspecification, I mean when system was not well specified to begin with. So maybe our loss function was not that well defined. Maybe constraints were not that properly set. Or maybe like we are working in the wrong hypothesis space to begin with. So basically, when we have a learning problem or a system, something was not defined properly that caused us to have multiplicity of those models towards the end. Then you may see in literature term model uncertainty. Compared to underspecification, it deals after the fact with a problem. So that's when we're already faced with these multiple models, with multiplicity, and then we understand what is a good choice here. So what should I do? Which model should I choose? Which aligns with my perspectives the best? And then there is term predictive multiplicity. It's kind of like a subset of a Rashomon set, if you think about it, and it works in the prediction space. So I can still have different models that rely on different reasoning passes, but give me exactly the same predictions on my data. But predictive multiplicity, it looks at those predictions and only considers when those are different. And why it is important? It's especially important when we want to do more individualized predictions. So let's say we look at the specific user and try to understand how fair or unfair a system is with respect to them. Then we care way more about predictions rather than reasoning paths that we got to that point. And for systematization, I would really recommend these two papers. They discuss a little bit in more detail some overview of the field and also possible causes, possible different reasons why the Rashomon effect and uncertainty can occur. And also today at 2 p.m. there would be another workshop that will discuss model multiplicity a little bit more. So that section is TQ05. Okay, one thing that you may already saw is with respect to medical domain, when I worked with not vision data, but kind of like this structured signal of EEG. But actually, this Rashomon effect is in a lot of places. It's basically everywhere when we think about machine learning. So for example, in tabular machine learning, there was this explainable ML challenge based on FICO data set that has to deal with predicting, do we have bad or good credit, should we get a loan or not? And it ran for some time, and essentially there were some models that was a little bit more complicated. But if you take the data set and then look at different models and different hypothesis spaces, and here I clustered them a little bit by more simpler and more complex one, but let me consider everything I can, like logistic regression, golden standard, which would be gradient boosted trees, neural net, which would be 8-layer neural nets, and 2-year additive risk model, which would be more interpretable model. So different models, and then look at test accuracy, a test AUC, and you can see that all of them perform approximately equally well, right? So it's another version of that Rashomon effect, where we took models from different complexity classes, but they give me the same performance. Let me give you more examples. So epistemic uncertainty in our prompts, let's say I made a prompt, please recommend me a restaurant on the main street. It's very generic prompt that can have so many different answers depending on how we specify and who the user is and what the intent is. First of all, which city, second of all, which type of restaurant. So there is a lot of multiplicity there as well. Second one, which might recall to your a little bit to your experience, let's say we are training a model, and then the only thing I will do, I'll just change a random seed. And suddenly my random seeds can give me very different models that also have very different reasoning passes. So for example, one of them in this example of two-part models can rely on actual linguistic rules, and those correspond to some intent of the domain expert that works with that problem. And second of those models can rely on spurious correlations. So it seems like something very harmful, which is just a random seed, but it essentially converges to very different points on our loss landscape. And lastly, which corresponds a little bit to, depending again on different features, but those that are equally predictive. Let's say I want to classify bird species. So it is possible to have two models where one relies on something like a wing pattern and another relies on beak shape, and they would be equally accurate and equally predictive well. So basically across tabular domain, images, and language, Rashomon effect is in a lot of places through our procedural or data inherent properties. And when we think about it in that way, if we can expect it to be anywhere, what does it mean? And I want you, if you would have to take one key message from this tutorial, that's what I want you to leave is that it changes almost everything we know about machine learning. We are trained to optimize for that one single model, for that golden answer. But what if we don't have it? What instead of we have multiple of them? Then which model do we choose? Which variables are important? Maybe some variables are important for one model and other variables are important for another model. How do we provide explanations? There are multiplicity of explanations, as long as there is also multiplicity of models. What is the problem complexity? We saw in the FICO explainable ML challenge that we have everything from simple model to neural net performing equally well. So what is the complexity of that problem? And one more question that we will explore today, what does it mean for trustworthy AI? What does it mean for all of this interpretability, explainability, fairness properties that we would like to have our systems? So basically, this Rashomon effect, it's kind of like a source of uncertainty because it is uncertainty. But also, I hope that you'll see that it's also full of magic and a source of possibilities. Because as long as we know it, as long as we are aware of it, we can design our algorithms better that could lead to better pipelines and machine learning algorithms. Okay, let me provide you with a little bit more formal definitions and also why this Rashomon effect can occur. So I'm going to take that yellow blob that you saw before and like stretch it on my x-axis, and it's going to be hypothesis space. And I'm going to look at y-axis at empirical or true risk. And that can be changed depending, like, are we working with more theoretical object, like true Rashomon set in my true risk, or with more empirical object, like I'm doing some experiments. And now I'm going to define a Rashomon parameter theta, which is essentially kind of like an error tolerance. It's some percentage of the loss on some additional errors that I'm willing to lose in order to get some more models in my set. It can be, for example, 1% of accuracy or 10% of my loss, like any amount that we are willing to define as a tolerance. It can be completely zero as well. And then I will look at all of the models that follow behind that threshold bar. And that will be my Rashomon set, that objects that we discuss of near optimal models. More formally, I'm going to work with empirical risk here. We take the optimal model with respect to empirical risk, which would be F empirical best. And we take risk of that model, add that theta to it, which forms my threshold. And look at all models that have empirical risk below that threshold. And that will be that Rashomon set objects that we're going to work with. If my loss is convex, it's going to be one single connected component. But in a lot of hypothesis spaces, like we don't have luxury of having convex losses, so it can come from different local minima as well. Or for example, if I work in discrete hypothesis spaces, then it will be scattered all over the place. Great, so now as we have a little bit more formal definition, why does it occur? And we already talked a little bit about underspecification, right? When our system was not well defined, about procedural multiplicity, when just changing random seeds due to our algorithm, we get different models. But I also want to talk about something a little bit data inherent, and more specifically about noise in our data generation processes. And why this noise is important. So let's think about any problems that we deal like in that we try to apply machine learning to in our human life. Like for example, will this person get a diabetes in 2 years? Or will I get promoted in my job in 2 years? Those are very interesting questions that we would love to know some answers to and be able to answer and predict. But data about humans are inherently very noisy. There are so many random choices in the world. Maybe somebody will change their diet. Maybe somebody will move to another state, or some other actions that can happen, which essentially introduce noise in our data generation processes. So then when we think about clean data generation process, and we will have this data on the right that comes from this clean data generation process, I guess it's left for you, right? And the data from noisy data generation process that come from a little bit more messy world that is around us, then of course we can expect more models to fit the data well if we come from the noisy data generation process. So, and indeed, if you look a little bit closer into some real world experiments, and I wish I had a way to generate data process, I'm going to model it by actually injecting noise into the system. But I want to say that I'm not advocating for it. It's just a modeling choice to look into having more noisy data generation processes. So then as I plot how much noise I have in that processes on x-axis and the size of my Rashomon set, which in this case we are working with a hypothesis space of decision trees on my y-axis, I can see that with more noise, the size of that set is going to increase. Meaning the more noisy my data generation processes are, the higher the Rashomon sets I can expect. And it's true across different benchmark data sets. But still, let's try to understand some intuition behind it even more. And what I'm going to do, I'm going to look into quality of the features. So let's say I have two features, G1 and G2. And by feature importance metric, I'm going to use a UC area under the curve with a label. So it's essentially how predictive this feature is to my label. So I have AUC for G1 and AUC for G2. And turns out that with more noise, as I have my data coming from a noisy data generation processes, better quality feature degrades in quality faster. So what does it mean? Let me try to take that Rashomon set analogy into space of my features. So let's say I have a set of relatively good features, and when it comes from clean data generation process, I will just step away a little bit by some amount of AUC. So then when I compare it to the set of features that come from noisy data generation processes, it kind of grows in size because the better quality features degraded faster. So this inflates that set tremendously and it becomes larger. So now let me take this back to the Rashomon set, and my models, they rely on features, of course, right? So, and now I have larger relative set of good features. That means that I have more models to choose from because they can rely on these small features. They can be worse in signal, but relatively, they're still equally good. So intuitively, this noise, it distorts our feature signals, which allows many different models to achieve similar performance for the same data set. So basically, that's why we can expect this larger Rashomon sets. Okay, this would be a great chance to pause and see if there are any questions. We can take them for a minute or two. Then we're going to switch to constructing and exploring the Rashomon sets. Okay, sounds good. Let's Judith to continue.
Okay, thank you, Lesia, for giving us very good intro about what the Rashomon set is and what is the Rashomon effect, and showing a lot of examples that the Rashomon effect can be everywhere. So after that, I will start with some methodology to construct and exploring the Rashomon set for different hypothesis space or model class. So you can see I listed several of them below, and I will cover them one by one. Okay, so in the section 1, you already learned what the Rashomon set is, and here is just another visual illustration. I will apologize if we use some notations differently, but hopefully you can get the idea through this visual illustration. So technically, when we define a Rashomon set, we need to have a model class first, or hypothesis space first, and we also need to have an objective function, or maybe you can treat it as a loss function. And usually, we find a model within the model class that minimizes the objective function as the reference model. We know its objective value, and we can add small epsilon to it and find the threshold theta. And the Rashomon set consists of all models whose objective value is less than or equal to theta. So I apologize for the ambiguity of the notation. So purposely we use a theta adder to the budget where the loss can go. And here we use the epsilon and use the theta to define the upper bound of the loss we can use. Anyways, the Rashomon set consists of all models within the model class with objective value less than or equal to theta. And here is the formal definition: let FREF be a reference model from a model class F. The epsilon Rashomon set is a subspace defined as all models within these model class whose objective value is less than or equal to theta. So the objective value comes from the objective function. It can be customized. So for example, in some case, we consider the misclassification loss as our objective function. Or maybe sometimes we consider the misclassification loss with some other penalty, sparsity penalty, as the objective function. So it can be customized. And theta is equal to 1 plus epsilon times the objective value of the reference model. And epsilon is usually a value that user specified. And we would recommend using epsilon as a very small value, so like 0.01 or 0.1, something like that. So which means you increase the 10% of the loss you can have compared to the reference model. So as long as you have an objective function, have an epsilon value, then you can technically define the rational set. And there is no limitation on the choice of the model class. But in this tutorial, I will start from the decision trees. The reason is decision trees are inherently interpret models, so human can understand what happened in the model. And more importantly, the first algorithm to construct the rational set for a non-trivial model class is for decision trees. So I will follow these historical and methodological progression before I move toward other model class. I believe everyone here knows about decision trees, so this is just a quick recap. So decision trees are inherently interpret models because their if-then based logical statements provide human understandable reasons for each prediction. So for example, this tree on the left is trained on a recidivism dataset to predict whether a defendant will reoffend in the next 2 years. And this tree makes the decision by asking the first question, whether the number of prior crime is greater than 3. If so, predict yes. Otherwise, ask the next question, whether the age is less than 26. So by looking at each decision path, you can understand how this tree makes a decision on the reoffending question. And traditional methods in decision trees literature use greedy split to grow trees, which leads to the suboptimal models. And here the suboptimal means that these trees are not very accurate. They cannot compete in accuracy with more complicated model class like gradient boosted trees. And also these trees are not very simple because the greedy methods tend to grow deep trees and the tree may have a lot of leaves, which may make it harder to understand. So recent studies aim to find global optimal decision trees with sparsity constraints. So they wanted the tree to be true optimal, which can compete in accuracy with complex model class. And also they want the tree to be simple, maybe just have 5 live paths like this one. And you may think this should be easy because the model seems to be easy. But actually, this is a very hard optimization problem, and only recently we observed some breakthroughs. And one direction is to formulate it as a mixed integer programming problem and then use mathematical optimization solver to solve it. However, these solvers are not designed for tree optimization, so they are usually slow. And another direction is to use the combination of branch and bound and dynamic programming. And these methods for this group can actually find the sparse optimal decision trees very efficiently. So this means we can find the true optimal model. We can have the reference model if we want to find the rational set. And with all these recent techniques, we can now ask a more challenging question. Can we construct the rational set for the sparse decision trees? And this paper exploring the whole rational set of sparse decision trees published in 2022 proposed the first algorithm tree farms to construct the rational set for sparse trees. So before I jump into how the algorithm works, I first want to put the goal here. So our goal is to find all good trees with objective value less or equal to theta. So we can find the optimal decision tree. We have the reference model. We know its objective value, which in this case we define as the misclassification loss with the penalty on the number of leaves. And we know the objective value for the optimal tree, and we add small epsilon to it, we can define the theta. So the tree farms algorithm consists of 2 steps. In the first step, it constructs a dependency graph from top down to create an overcomplete space, which implicitly contains all good trees. And in the dependency graph, the node represents a subproblem, which is defined by a subset of the data. And the edge represents how a parent problem is split into left and right subproblems. I know it's very abstract. Let me show you an example. So usually we start with a root problem, which is annotated as a black dot. And in the root problem, it consists of all the data points because we want to construct the rational set for the entire data set, right? And you can see the ID of the root problem or the bit vector associated with the root problem contains all ones, which means all data points in our data show up in this problem. And you can use whatever conditions in your data to split the root problem. And maybe we use price less than 2, maybe we use age less than 26. And using different splitting conditions may end up with different subproblems. And you can continue to solve the subproblems. And sometimes different splits may end up with the same subproblem. Then it's already in the graph. You can connect to that subproblem. So after growing this dependency graph, you actually construct a space that contains all good trees. But not all trees in this dependency graph are actually good. So we need to be careful about extraction. So the second step in the tree farms method is to prune the dependency graph and extract good trees from bottom up. So we want to make sure all extract trees are actually in the true rational set, which means their objective value is less than or equal to theta. I will not go to too much details, and if you're interested, feel free to check out the paper. And the tree farms algorithm contains 3 key ingredients. So first of all, it uses a dynamic programming for computation reuse. As I introduced in the when we construct the dependency graph, you can see sometimes different splits may end up with the same subproblem. Then you don't need to store it again. You can reuse what is already in the graph. And also, the tree farms algorithm uses the branch and bound to efficiently reduce the search space. So it uses in both step 1 and step 2. So when we construct the dependency graph, if sometimes the lower bound of a subproblem is not good as the upper bound, then you don't need to grow the dependency graph along the subproblem. And in the pruning stage, it can also help you to use the lower bound and compare it with and if the lower bound of a subproblem is already greater than the theta, which means no matter what you do, this problem will not be part of the rational set, then you can get rid of it. And the third key ingredient in the tree farms method is model set representation. It can efficiently extract and store trees by comparing the objectives. And combining all these techniques, the tree farms algorithm can find millions of good trees within minutes. In the paper, they compare tree farms with 4 baselines. So BART is Bayesian additive trees. You can get different trees by sampling from its posterior distribution. And another baseline is random forest, which consists of many different trees naturally, right? And the other 2 baselines are training cart on the bootstrap samples of the original data set and train the optimal decision tree on the bootstrap samples on the original data set. So on the Monk2 data set, the tree farms algorithm can finish constructing the rational set in 46 seconds. So they run baselines for 46 seconds as well. And in 46 seconds, BART can find 3 trees in the rational set. And the random forest finds no trees in the rational set. And cart with bootstrap sampling can find 7 trees in the rational set. And the optimal tree with bootstrap samples can find 15 trees in the rational set. And compared to tree farms, which probably enumerate all good trees in the rational set, and it can give us more than 105 million unique trees. So it's quite a lot, right? And these patterns not only show up for the Monk2 data set, they also try a bunch of different data sets, and this pattern holds for other data sets as well. So the tree farms algorithm can really find orders of magnitude more trees with good performance in the same time limit. Then a natural question show up. So there could be so many different trees. How do we pick the one that we should use? Obviously, as a human, we cannot digest these many trees, right? I cannot hand you a JSON file and you look at the trees one by one, so it will be very inefficient and very user-unfriendly experience. So after the development of tree farms algorithm, the team also create a visualization tool called TimberCheck. So this visualization tool can help to support user interaction. It supports navigating user-preferred model in different ways. For example, you can find a desired tree by specifying the splitting conditions using the sunburst plot in the middle. So for example, for a data set, if we know that we only want to split we want the first question to be asked is whether the number of prior is greater than 3. Then we can click that condition, and it will then only show the tree that split using this condition in the top of the tree. But sometimes we may not know which condition we want to use, right? Then how can we use this visualization tool to help us? So then in this case, we may consider use the search panel on the right to help us find the tree we want. So for example, it lists the range of the accuracy the tree can achieve. And maybe we want to get rid of some, we want to only look at the tree with a relatively higher accuracy. Then we can drag this bar to only look at those trees. Or maybe we want a simple tree. Then we can specify the depths we want to use. So maybe we only want to find a tree with 3 layers, then we can specify the depth to be 3. Or maybe sometimes for some fairness consideration, we don't want to use features such as sex equals to female. Then we can uncheck this feature, and the sunburst plot in the middle will be updated, so it will exclude all the trees who use this sex equals to female in the tree. And we will play with this tool later in the interaction session, but I want to give you a heads up how this visualization tool looks like. Okay, so then the natural question we will have is that, can we expand the rational set to other interpretable model classes, right? So sometimes we don't want to play with trees. We want to use other model class. Then can we equip them in the similar way as we equip the sparse decision trees? And the answer is yes. Now we have the algorithms to construct the rational set for generalized additive models and scoring systems. And I will start with the generalized additive models. So a GAM model, a generalized additive models, usually we call it GAMs. A GAM model takes this form. It is the sum of the component functions or shape functions for each feature. And from left to right, G is a link function. If we are dealing with a regression problem, then G is an identity function. And if we are dealing with the classification problem, then G is a logistic function. And W0 is the intercept, and Fj, Xj is a component function that only operates on feature J. And let's look at an example about the GAM model. This is a GAM model trained on a diabetes data set, and each subfigure represents a univariate component function. And I also zoom in on the component function for glucose concentration here. So you can see how different value of the glucose concentration can contribute to the final prediction. And you can see several jumps in the shape in this component function, and maybe it disclose some abnormal patterns in the data or some weird patterns that may be introduced by the model. Anyways, from this example, hopefully you get a concept like what a GAM model will look like. And the GAM model is very interpretable. It is the sum of the univariate component functions. And each univariate component function can be visualized through a 2D plot. So just like this 2D plot, we can understand how this feature contributes to the prediction. And also, a GAM model is very powerful, even though it seems like it has a linear form. But each component function can be nonlinear, so it's very flexible. It's much better than the logistic regression. And the GAM model can be trained using boosting or other modern machine learning techniques. So the example I showed before, actually, the GAM model is trained on by using the boosted decision trees. And if we divide continuous features into bins and find weight for each bin, then the component function is a step function like this. Okay, so there are several different algorithms can help us to find the generalized additive models. So how can we do the rational set? How can we do the rational set for this model class? So this paper proposed a method to approximate the rational set for sparse generalized atom models. So first of all, they treat the GAM as a bin step functions for each feature. So the entire model then becomes a linear model. We just need to find the weight for each bit. And they define the objective function as the log loss with the L2 penalty on the weights and L0 penalty on the number of, because they want the model to be sparse. And once the L0 term is fixed, what we left in the objective function is only log loss and L2 penalty. So in this case, the objective function is convex, and the rational set is a convex set. However, unlike what tree farms did for the sparse decision trees, generalized atom models has a continuous space. A small perturbation in weight can actually give you a model in the rational set. And we cannot really enumerate all the models in this continuous space. So this paper proposed a method to approximate the rational set by using an ellipsoid. And the key here is that you cannot construct a random ellipsoid, say this is the rational set. You need to find the ellipsoid carefully. So first of all, the ellipsoid should be enlarged to contain a lot of well-performing models. So it should be large in volume. However, you cannot enlarge the ellipsoid with no restriction, because if it is too big, then it contains all good models in the true rational set, but it will also contain models that may not perform well. So at the same time, you need to make sure the models in the ellipsoid are actually in the true rational set. And with these two contradictory goals, the paper formulate an optimization problem, and they solve it using the gradient descent to find the ellipsoid. And once the rational set of the GAM model is approximated, we can also visualize them. So here, each red line, each red curve is actually one model sampled from the rational set of GAMs. And here we show 100 different shape functions. And you may think they look very similar, but actually some of them could be very different from others. But the thing is that all of these 100 models are quite accurate in terms of the log loss with the L2 penalty. And so once we have the rational set of GAMs, we can also allow users to select the model that align with their needs. And we find that this experience for the GAM model could be different from the tree model. Let me show you an example. So for example, this is one model from the rational set for the blood pressure to predict the diabetes. And look at this component function. You may think, okay, it looks fine, but something maybe not that natural, right? So maybe the component function should be monotonically decreasing with respect to the blood pressure. It may align better with the domain knowledge. But this one, we can observe a jump around 60 when the blood pressure is around 60. So is that possible for us to find a model that actually has a monotonically decreasing pattern for the blood pressure, but still perform well? Once we have the rational set, we can actually find such model by solving a quadratic programming problem with linear constraints. And this will give us the desired shape function colored in yellow. And because the model is found within the rational set, the model can be still quite accurate. And this is one of the use case. And another use case may be when we look at this component function, we find this is not that ideal. Then we may have some preference. We hope the component function can look like something like this. Right, but sometimes what we prefer may not be a model within the rational set, which means this red curve may not be a model in the rational set, may not have very good accuracy. Then what we can do? Actually, once we have the rational set, we just need to solve a quadratic programming problem with a quadratic constraints. Then we can find a model that within the rational set that is close to what user prefer. So the green curve is something that after solving this QP problem, we can get. And this green curve somehow balance the user preferences with the model found by the algorithm. And these are the two different user case that we can have once we have the rational set for generalized active models. Any questions? Okay, so we talk about trees and generalized active models, and then next we will talk about risk scores. Some of you may not familiar with risk scores, but it is actually very simple. It's just a sparse linear models with integer coefficients that predict risks. And this is the entire model. And risk scores, because it's very simple, it is widely used in clinic. And nowadays, still a lot of diagnoses are based on the scoring system like this. And in this example, it estimates the risk of breast lesion being malignant. And you can simply check 5 factors of a patient and sum the points up to get a score and check the risk using the table in the bottom. And the model is easily understood and memorized, so that's why it is very desirable for high-stakes decision-making problems. And so recently, actually, there is also an algorithm to find the risk score like this. It's called fast risk. And during the process of finding a well-performing risk score model, they actually provide a lot of alternative models. They are still risk score, but they are also equally they are also well-performing. So naturally, they consist of the rational set. And in the fast risk method, it aims to find the models that minimize the logistic loss, and at the same time, it wants the model to be sparse. So we only need to check fewer conditions in the top table. And also, they want the model to have integer solution, because if we have integer solution, it's easy to calculate. Doctors can calculate it without using the calculators. And also, they want the risk score to satisfy a box constraint to restrict the range of the coefficients. So we want to make sure these integers are small values. It's something like 1, 2, 3 instead of 111, 215, something like that. So they want the integer to be small as well. Okay, so they want to solve this optimization problem. And the algorithm fast risk uses 3-step optimization. So in the first step, the algorithm solves the sparse logistic regression by using beam search to select the best subset. And then in the second step, the algorithm finds many near optimal sparse logistic regression solutions by swapping features. So in the first step, you have a best subset. And in the second step, you swap one of the feature in your best subset with another feature that is not selected. And this can create a lot of different best subsets, but they are not necessary to be the true best, but they are like good subsets. And then you optimize them very quickly to get the coefficients for this new subset. And as long as the new loss is no worse than the current loss by a predefined threshold, the algorithm adds a continuous solution to the candidate pool. And this means you will have a pool of good candidate. And then in the third step, the algorithm runs runs the coefficient to have the integer solution. So for each candidate in the candidate pool, the algorithm scales the continuous solution using many values of a multiplier, and then run the scaled coefficients one coordinate at a time to get the integer solution. And they do this for all candidates in the candidate pool. So this will end up with many different risk scores. So here is an example. You can see I just grab 5 models from the paper, and you can see they are different. They look at different conditions. They look at different. They use different integer values, but all of them have AUC above 85%, I think. Okay, so after we introduce the methods to construct the right set for different interpretable model classes, I guess you may want to know, like, how about neural networks? This is like widely used nowadays, and why not construct the rational set for neural networks? Of course, this is a very interesting question, and this is like a domain that many researchers are exploring right now. But it is very challenging because neural networks can have different architecture. It has a continuous base, and a small perturbation can give you different models. But what do we mean about the rational set for neural networks? So as Lesia mentioned before, one natural way to construct the rational set for neural networks could be using different random seeds. But this is not very systematic because you can try like different random seed and not necessarily the model trained by using different random seeds actually give you different models, because small perturbation don't really mean a lot, right? So sometimes we want to have like more different models, but they perform quite well. So in 2024, she et al. Proposed the paper to find an empirical set through the dropout. So they train the neural network first and take the fixed train weights. And at inference time, they sample a dropout mask and create a new model by multiplying weights by the dropout mask. And this can create like different models in the inference time. And they only keep the dropout models whose loss increases stays within the Rashomon tolerance. So this is how they do it. And they want to use these to study the predictive multiplicity, which is like different models may give different individual data points, different predictions. And then what we can do with it, because sometimes we not only want to take a look for the average of the performance in the data set, we also want to study the individual prediction. So they try to use the Rashomon effect in the neural network to study the predictive multiplicity. And a different way to approximate the Rashomon set for neural network was proposed by Donnie et al. In 2025. They actually consider the proto-PNet. They do not consider arbitrary neural network. They consider a specific type of neural network, which is called the proto-PNet. And they also like train the proto-PNet first, train one model first, and they fix the trained backbone and the prototypes, and then they approximate the Rashomon set only over the last layer weights by using an ellipsoid. So similar like the generalized additive models, which approximate the Rashomon set using the ellipsoid, they construct the ellipsoid in the last layer of the proto-PNet. And this will give them different combinations about how to use the prototypes trained before. Okay, then we cover all the model classes that I want to share. Any questions? Yes.
You sample models this way, they are not going to be IID, especially the conditions.
Exactly. So this is the thing that is between the Rashomon set and the Bayesian statistics. So in rational set, when you sample the model, it's not necessarily IID. But in Bayesian, it's like if you sample from this. So the thing is that if you just want to pick the model that you can deploy in the real application, it doesn't matter. Because you can like troubleshoot like what feature is you used in the model, like what is like the decision logic. However, if you want to calculate some statistics, then this could be problematic. So just be cautious if you want to use the sampling model from the rational set and calculate some test statistic, be cautious about it. Any other questions? Okay, so I think next we can go to the interactive section. And hopefully I can show you an example how to use the yeah. So how can we do it? You can just enter. But I cannot type anything.
Oh, you cannot type.
Yeah.
Oh.
So how can I do it? Wait, no, it's not this.
Hmm?
We cannot even go there.
This one.
No, it's not this one. Wait. I think something is wrong. But I cannot like.
Oh, I can see your
Oh,
pointer
okay.
now. Perfect.
Wait. I think I go to the. Can I just type it again? Can you just give me? Okay, so previously I already shared like once we have the rational set, this kind of visualization tool could help us to select the model we want. So there are two different ways to use it. So this is example on the compass data set, which is the recidivism data set I mentioned before to predict whether a defendant will reoffend in the 2 years. So for example, if we know which feature we want to use to construct the decision tree, then we can, for example, select, say, I want to use the number of prime is greater than 3 to split the top problem. Then I can click it. Then each gray bar here is actually a decision tree. You can see that split the top problem using these specific conditions. And for example, if I want to specify the next question I want to ask, maybe age less than 26, then I can click it. Then each tree here actually has the second question asked, the age less than 26. And I can click it to get the tree window. And I can also drag the tree window so that we can compare different trees. It's not very easy to do it here, but I think you should be able to do it on your website. Anyways, and you can also open more trees if you want. And wait, so I just okay. So if you like this tree, you can click the heart to add to your favorite. Is this a heart? And also you can left a comment about the tree. So for example, you wanna you look at a bunch of different trees and you will say, okay, I probably wanna keep this one, keep that one. Maybe you can just write a comment for each of them. Okay, anyways, as I mentioned, sometimes we may not know which splitting conditions we might want to use. Then we can use the search panel on the right to help us. So for example, I want to look at very accurate trees, then I can drag it here. So all the trees should have the accuracy above this threshold. And also, I may wanna say, okay, so I can give more range for the accuracy, but I only want to look at the not many deep tree. So so I can uncheck depth 5 and 6 to look at simple trees. And similarly, we can like specify the features we want to use. So for example, sometimes for, as I mentioned, for some fairness consideration, we may not want to use sex equals to female. Then we can uncheck it, and all the remaining tree in the sunburst plot will not rely on this feature. So in the rest of the time, you can play with this tool with your neighbors. And there are a bunch of different data sets that we've already uploaded to this demo. So feel free to play with different data set and try to collaborate with your neighbors. And we will resume the tutorial in 5 minutes. Okay. You can open the link just using, this is like publicly available, so you should be able to type this link and open it on your laptop. Yes.
I was wondering if you knew if like in practice where like this is used for predicting specific like words, if they use like the generation of rational sets on the message model, because from what I understand, they use like numerical reflection, like a bit has been applied to the actual model that like the purpose software uses.
It is not. So we are also like recommending, like if any of you want to try it, feel free to try it on your data set. So Compass is still like a black box model. It's still we think it's a linear model. But the thing is that we believe the accuracy about that linear model should be similar to like the tree model. But since this is like black box, we never know like what it is really happening inside. But you know, like Compass data sets have a story that maybe could be biased towards a black debate because no one knows whether race is specifically the model. But the thing is that sometimes, of course, we can easily get rid of that kind of sensitive feature before fitting the model. So for sure, it will not be used, but sometimes we may not. But the thing is that, for example, if you have this kind of rational set for whatever model policy construct, then you can check which feature is used in the model you want to deploy. And say if race is used in the maybe that model, you probably won't use it, right? You can find there are so many well-performing models. Why you stick with that one using race? You can choose other models. So, but yeah, it is not used in the percent of, but hopefully one day people will think about this rational effect pipeline when they try to deploy the machine learning model.
I just had another question. But like, does this also help deal with like, I guess like features like being encoded? So I mean, like for example, even if you remove like the like gender like feature, like the model might still like blur the features like other. Is that something that?
Yeah, for the correlation, right? So usually what you can do is that once you have the right model, you can actually calculate the fairness score for each model. And actually, I will talk about later that how the right models that can actually give us a lot of candidates who have different level of fairness with respect to different fairness definition, and you may want to pick the one that is good with respect to the fairness criteria that you want to see. So the thing is that if you don't have the rational set, then you need to train, for example, one model, you calculate the fairness score, and you may find it's not that good. We need to optimize it again with extra condition. But this process can take a while. And you may need to retrain and reformulate the problem many times until you get a model you think that is reasonable. But the rational side is that we find all these good models. and we create a constrained search space. And then you can just search within this to find a model that satisfies the conditions. And fairness could be one condition, there could be other conditions. Like use specific feature, use the feature in the right order. Also like not only good in terms of accuracy, but also good for other evaluation metrics like F1 score, balance accuracy if you have imbalanced data set. Or maybe it should also be a model that satisfy other domain constraints. So then you don't need to reformulate the problem and re-optimize resolve the optimization problem. It is already there, just pick it up.
Thanks.
Any other questions? Yes.
As for neural networks, right, because they are less explainable by nature. So actually with the Rashomon set, how would you then choose the right model to make use of? You have to do sorts of testing on fairness, etc.
That is a really good question. So for neural network is very tricky because it's naturally a black box.
Yeah.
There are actually several interpretable neural network model classes. So one is like the prototypical network, and it learns the prototypes first. And your prediction is only based on the prototypes you learn. So then you can know like which prototype you look at once you have it. And another interpretable neural network model class is the concept bottleneck models. So basically you have the input image, you go through some backbone, like either it's a VASNet or it's a VIT, and you predict the human annotated concept first. So the concept could be like blue color, or concept could be like peak of a bird, or like fur, whether fur is show up in this image. So you predict these kind of concepts first. And then you use these concepts to predict the class of the image. So you have this kind of intermediate data, you know how to predict it. So for the rational set, if you construct a rational set for arbitrary neural network, then it's very hard to do this kind of like human evaluation of troubleshooting. But if you construct a rational set for the prototype, you can see, okay, so maybe it relies on the wrong prototype that we should fix it, or we use another one. But still right now, for the prototype, rational set is quite limited because it only considers the last name, the way of the last name. So this is like an overly research direction that is there any better way for us to do. And for the concept model, there is a paper, it's not published yet, but it can like say for each model in a rational set, try to use different subset of the concepts to make the hyperprediction. So it relies more on the data, the input data, and also the model stuff. Any other questions? Pause for 5 minutes, just for okay. Okay, so maybe we just pause for 5 minutes for a break, and then we will resume the at 9:45. Should I go back to slides? Yeah, okay. Okay. What? Okay, so in the previous two sections, we learned what is a rational set, what is a rational effect, and some algorithms to construct the rational set for different model classes. So in the rest of the time, we will talk about what benefits do we get once we have the rational set? What kind of implications we can get from the rational set for trustworthy AI? So I will cover the three parts: fairness, robustness, and privacy. So recall that usually we need to have a predefined hypothesis space to talk about the rational set, and the predefined hypothesis space could be variable. It could be like binary classification tree. It could be like generalized additive models. It could be risk scores. It could be neural network. And the rational set are a subspace within these hypothesis space, which consists of all models whose objective value is very close to the reference model. Or maybe you can think about these are models who are which are very accurate. And usually I just use like the red dot in the middle. Maybe we denote it as the F star, which means it could be the optimal model. And it's actually a reference model here as well. So once we have this rational set, we can actually get many different models from this set, different from the optimal one. And we may hope that some of them could be like robust with respect to some kind of like adversarial attack, or robust with to some kind of distribution shift. And we hope some of them could be more fair than others. And maybe some of them could be like more privacy preserving models. And there are a lot of study try to study how for example, the fairness or like or privacy once we have the rational set, or how the fairness interact with the rational effect. And many papers actually find models with similar accuracy can have very different fairness outcomes. And these papers also advocate to use rational effect as an auditing tool for fair decision making. So we not only just find one model and use it directly, try to evaluate other models with similar level of the accuracy and see whether one of these other model could be better in terms of the fairness criteria than the original model you have, and try to use the one that can achieve a good balance between the accuracy. And in addition to these set of analysis on the fairness and the rational effect, there are other papers not only consider accuracy, fairness, but also how the rational effect can be applied to the individual data point. So they consider the arbitrariness as well. So arbitrariness means that different models may give different prediction to a single data point. Then which prediction we should assign to this data point, right? And the paper published in 2023 finds that the fairness intervention, which try to help in both accuracy and group fairness metric, can actually increase the predictive multiplicity, which means each individual maybe say 50% of time receive the positive prediction and 50% of time may receive negative prediction. Then which prediction we should really assign to this individual, right? And they find that if they average the ensemble over multiple fair models, they can actually reduce the individual arbitrariness. So if they ensemble many well-performing fair models, then they evaluate it on each individual data point, and these individual data points may receive more consistent predictions. And another paper also finds a similar pattern, and they find that if you use the ensemble plus the abstention, you can actually reduce these individual arbitrariness further. So this means, for example, you have different models, they can give different prediction to the individual data points, and you find sometimes some data points are very likely to always receive like 50% positive, 50% negative, then we don't evaluate these data points. We only evaluate the data points that the model is more confident about. Then in this case, it naturally solves the fairness problem. It naturally can find a model with good fairness evaluation on the rest of the data without any fairness intervention. And there are still a lot of ongoing work to discuss the relationship between the fairness and the rational effect and how the rational effect can be used in terms of the decision making. And in addition to the fairness, some research also find that rational effect is related to the privacy. So this paper showed that the differential privacy training can actually induce individual arbitrariness and find stronger privacy increases instability. So if you train the model with the differential privacy, so you need to have some kind of the randomness in that, then this can actually increase the possibility of the individual arbitrariness. So how to balance the accuracy and the privacy, or maybe utility and the privacy, and how the rational effect can influence the privacy is also an open question. And previously, we just talked about the rational effect and the relationship with one specific trustworthy metric. And there is also other work to study the multiple trustworthy metrics with respect to the rational effect. And this paper finds that the rational set can naturally contain robust, privacy-preserving, and fair trees, even without explicitly optimized for these metrics. So they create the rational set of decision trees, and they study 7 different trustworthy metrics, which covers the robustness, privacy, and fairness. And they see whether the rational set can already contain good trees with respect to these metrics one by one, compared to the trees optimized for these metrics. And they find once the optimal one tree in the rational set is attacked, there could be other trees in the rational set which can still perform quite well on the adversarial data set. And they also find there could be trees within the rational set that has a quite good fairness score, like the equalized odds, for example, is one of the fairness metrics, and they can find a good trees with respect to this metric compared to the tree optimized for this specific fairness metrics as well as the accuracy. And they also find that sparse trees within the rational set tend to be more privacy preserving because it's more sparse. It relies less information from the input data. And another paper also tried to study the rational set and multiple trustworthy metrics from the conceptual perspective. And they find the rational set is in general very stable with respect to small distribution shift. And the rational set is actually providing a source of the reactive robustness. This means that once you have the rational set of models, if you attack one model in the rational set, the other model far away from the attacked model can still perform well on the adversarial robustness. And this means that if one model is attacked, you can try to find another model in the rational set to replace this model. And but on the other hand, they find the rational set presents a risk of increased privacy leakage. So for example, if you provide more models from the rational set to audience or to the public, and the attackers can actually aggregate the information from multiple models to try to reconstruct the data that used to train these models. So if you release more models from the rational set, you increase the risk of the data leakage. So they present the Rashomon set as a duality. There is a duality fact within the Rashomon set, that it's good for the robustness, but may hurt the privacy. And there is this, as I mentioned, this is still like the open research area that need a lot of exploration to study how the Rashomon set can really affect the trustworthy metrics like fairness, robustness, and privacy, and maybe more in the future. Okay, any questions about these metrics and the relationship with the Rashomon effect? Okay, so next, Lesia will talk about the implications for other trustworthy metrics.
Thank you, Trudy. As you might remember, we chatted about Rashomon set being source of possibilities. So basically, our strategy is like this: compute once and then align with whatever you need. We computed Rashomon set once, we need fairness, we align with fairness. We need robustness, we can align with robustness. So we can search the Rashomon set to find some properties that we would like to have, essentially, given our needs or given some problem constraints. And other three metrics that I would like to talk about would be interpretability, explainability, and feature importance. And you might already understood from this tutorial, we do care a lot about interpretability. And reason for that is because we work a lot with domain experts following real-world problems. And whenever we work with them, they often ask a question: why model did that? What happened? Is there a problem? So we need to provide them some reasoning, and that's like where interpretable machine learning shines. And there are multiple benefits to using interpretable models. For example, let me give you an example again from medical domain. And there is an FDA-approved algorithm that detects a leak, like a brain, when there is blood in brain, essentially, and it fails, and it doesn't know. Like, researchers do not know why. Researchers who designed this algorithm. So they spent countless hours trying to figure out what happens. And essentially, they said, you know what? We don't know. We actually have no idea what is happening. But imagine that instead of that black box model, interpretable models would be used. And I cannot claim that it would be easier for them to find the problem, but it definitely would be easier for them to troubleshoot because they will see the reasoning behind the decisions. And when you think about interpretability, there are so many more benefits. We can align with domain experts. They can give us feedback. We can enable trust to the user. And here I want to be really careful because very often we say it's equals to trust. It may not. It may actually create distrust. If you look at the model, it relies on features we don't want it to rely on. But it gives us a chance to choose, do I actually trust this model? And also it helps identify potential biases, right? So I can look at my data and see if there are any problems or issues with it. And it can give me complete set of explanations. So let's say I want to provide users reasons behind some decisions. So then instead of explaining and having different reasons, I can be true to my model. So there are multiple benefits. But then we don't use those models very often. And essentially, we believe maybe some people just have preferences. Like, for example, if I'm really good with random forests, I really like this algorithm, I can use it everywhere. But we believe there is another reason, which is that there is a long-standing belief in community about accuracy interpretability trade-off. And the belief is like that. If I'm going to plot interpretability on x-axis and accuracy on y-axis, then all my black box model, complex models, will be really good in accuracy and, of course, bad in interpretability. And all my good models will be really good in interpretability, all my white box models, but really bad in accuracy. And you know what? The Rashomon set actually helped us prove that this belief is wrong. And I'm going to walk you through some intuition to show why for a lot of actually high-stakes domain data sets, actually we can expect that there is no trade-off. And we already saw it in a FICO example, if you recall that plot, where different models performed equally well. So I'll be honest that white box model may not be any model, any logistic regressions that you find. You may specifically need to optimize for it and design regularization constraints. But what we're going to focus on is like on existence. Does there exist a model? Will that empower us to go and spend that time on designing those regularization constraints? And remember, we talked a little bit about having true risk in order to define the Rashomon set. So we're going to define Rashomon set based on this theoretical concept. So we're going to, again, have our hypothesis space. And now we're going to look at the true risk and best model in class with respect to true risk, add some tolerance errors that can be 0 again, and look at all model below that specific threshold that is given to us. And I'm going to also assume that my hypothesis space is kind of interesting. So it's not that easy. It's a little bit complex. So it has whole models in it that will be my yellow blob, but also it has simpler models in it. And simpler could have different definitions. For example, it's a models with added L1 or L0 regularization. Or as in this case, I can have fully grown decision tree will be my old models, and then sparse decision tree will be my simpler model. Or I can have neural net of 10 layers, a neural net of 1 or 2 layers that is more understandable than if we have not like very wide neural networks. So it could be a simpler model as well. So anyhow, these simpler models are somehow hidden inside that whole hypothesis space of other models. And turns out, if I look back at the Rashomon set, if the true Rashomon set contains at least one model, and I don't need to know it, I just need to know that it's large enough to contain a model from a simpler space, then I can optimize for a simpler hypothesis class. Meaning, if I think about 2 models that are relevant here, one would be my performance on a true risk. That would be my ideal models that I would love to get. And it will be the yellow star here, F all true on true risk. And then I optimize for my simpler hypothesis space empirically, given my data set. These models will not be that far away in a true risk. And actually, we give a formal statement for that. So we give a formal theorem where we bound our true risk of that simpler models that we optimize on empirical data with true risk of that best model in the class, plus some complexity terms. And let's look at those complexity terms. Upper bound depends on the Rashomon parameters. It can be very tiny, so it's not that complex. And lower bound depends on the complexity of a simpler hypothesis space, which is nice because it's tighter than majority of statistical learning bounds that would depend in this case on the complexity of the yellow class, not the blue class. And recall what the statement for that was? If the Rashomon set is large enough to contain a single simple model. So basically, larger Rashomon sets give us good generalization properties of a simpler hypothesis spaces within those Rashomon sets. We talked about true risk and true argument, but the same is true for empirical risk. And let me give you intuitively why this could be happening. So I'm going to make an approximating assumption that definitely is true for trees, for example, because trees is a universal function approximator. But I'm going to assume that inside of my hypothesis space, I have my scattered simple models, but they approximate within some distant delta my complex models. So then again, if the Rashomon set is large enough, it would contain more simpler models within it. And we can think about it as formal argument in terms of packing number. And it is a number of disjoint balls that I can fit in this volume of the Rashomon set. Then the Rashomon set will have at least packing number of models. So then I can use this empirically to find at least how many simpler models I would expect this more complex object to contain. And these two proofs, one is based on empirical risk and another is based on true risk, are actually providing us a good understanding of what has been known in literature since the 90s. Since 90s, researchers have been saying, if I look at simpler models, they actually perform quite well, but it was hard to say why. And now we have an actual way to prove it using Rashomon sets. And of course, here is a FICO reference that also confirms our hypothesis that there is no trade-off, at least for this data set for sure, because we can look at complex model and at simpler model that they achieve similar performance. Okay, great. So how about explainability then? We talked a little bit about interpretability, but sometimes we cannot avoid using black box models. These are powerful models and there are domains in which we have to use them, but we still would like to understand some reasoning behind them. what does Rashomon effect means and for explainability, where by explainability I mean when given a single model, I try to understand reasoning in a post hoc manner. So I use a set of tools to try to approximate my local behavior or some other way in which I define my explanation to find some reasoning behind models' decisions. And Rashomon effect here occurs on two levels. On one level, I have multiplicity of models that we talked about. But on another level, I have multiplicity of explanations. And here, I would like you to think a little bit about that intent again, where I have different users, different stakeholders that may have different needs depending on my problem. And then when I have multiplicity in explanations, different stakeholders can align with those explanations differently. So for example, if I have some local explanations, they can choose one that satisfies more their initial biases or something they are looking for. And that will be true for like local explanation methods. Or if I imagine counterfactual explanations, where the goal is to provide with some actionable, editable inputs, changes to my input, so that I can cross the decision boundary. Basically, let's say if I was denied a loan, then I've been told, please increase your income by $500, and then we're going to approve you for a loan. So that provides me actionable feedback that counterfactual explanation can give me, but I can have multiple counterfactual explanations, and they can have different properties. So for somebody, increasing income is more feasible. For somebody, reducing loan amount is more feasible. So that then allows for different stakeholders to choose what they are looking for from that explanation. And then second source of uncertainty is, of course, our model's uncertainty. And here there are unlimited space of possibilities how we can use it. But I would like to talk about, I think the most important problem with explanations is like validity, making sure that explanation remains faithful or truthful. Because remember, it's very often just local approximation. So if I slightly change my model, it can actually change. And one way is that we can like take use of the Rashomon effect is to design algorithms that actually are aware of it. So for example, if I use counterfactual explanations as an example, let's say that I had one input data point and I produce explanation for it. And then I had slight model change, and now my explanation remains invalid. So instead of like reacting to this, I can be proactive and I can design an algorithm that is robust to begin with and will give me explanations that is robust to Rashomon set, for example, to ellipsoidal Rashomon set or to trees Rashomon set, or however I choose to measure it, and it will provide me explanations that then will not be that fragile to subtle model changes. That explains a little bit more about explainability, but also variable importance. Let's say we have two models, and model A relies on feature 1 to 3, and model B relies on feature 4, 5, 6. So which feature is important then? And very often statisticians who work with real-world data actually are faced with these questions. And we believe that taking advantage of the Rashomon effect is actually really helping here. So for example, we can design algorithms, as in this case, it's called Rashomon importance distributions, and they utilize Rashomon effect, specifically using tree farms and bootstrapping, in order to give you feature importance metrics that are Rashomon set aware. So then in a way, it's not very accurate, but I'm going to use this analogy as giving you feature importance more inherent to your data rather than a specific model. Or let's say that we can look at model class reliance, which would be a range of variable importance values. So then I don't have a specific value, but I can have a whole range of values. And then I can see for different features how variable they are based on that range. And actually, computation of model class reliance is not that difficult as long as we have that Rashomon set given to us. We can just look at the minimum and maximum over a set of good models or over the Rashomon set of the reliance value, and reliance can be computed in different ways. For example, in this case, we can look at an increase in prediction error when we perturb our data set a little bit, but we can use other methods as well. Okay, hopefully by now you're a little bit convinced that Rashomon sets and effect impact a lot of problems in machine learning. So we would like to touch a little bit on what does it mean, and also like what should we do next. So we think that it's very important policy implications that concerns Rashomon effect. So first of all, we truly believe that the Rashomon effect itself is almost like a policy object. Imagine that you release a few models and suddenly you become less private. That is a concern. So whenever we decide and describe our algorithms, we need to be aware of that we cannot that easily swipe our models because we leak more data. So we need to be aware of that when we're designing our policy procedures. Second of all, we do believe that it should be included in our education. Very often we are being taught about single golden answer pipelines, but then when we go and use ML in real world, we are faced with this model uncertainty, and getting to know it in advance would be really helpful for us to work with real world applications. Third, as we already see, there is actually a theoretical proof using Rashomon sets that very often interpretable models performing as well as black boxes. So this gives us a set of domains where we can demand actually interpretable model because we know it definitely exists. So we can then spend time and resources of going and finding it. And lastly, it allows us to verify claims about different properties of the models. So let's say we are given that Rashomon set it contains 1,000 models. We can simply go one by one, enumerate them, and check different properties we are looking for, and then select the best models that we want. That again connects back to this Rashomon set being as a policy object because it allows us to align with our needs at hand. Okay, great. And then let me chat a little bit about future directions and open problems. And there are actually a lot. So this slide doesn't even remotely cover what we can work on as a community and what we continue to work on. But we believe these are the most important necessary steps to continue and help the community to expand current work. So one, we talked a little bit about noise being the source of the Rashomon effect. But there could be other reasons. So maybe there is some properties between feature redundancy, collinearity, and random noise that we don't know yet. Maybe there are some properties of data generation processes, especially for language models or for vision images or for some, even for tabular data sets that we didn't consider it, that will give us also larger Rashomon sets. Second of all, how do we find this and represent these large Rashomon sets at scale? We talked about algorithms for decision trees, but even then we can have like a billion of models or millions of models. So some summarization techniques may be needed. On the other hand, we talk about algorithms for finding Rashomon sets for neural nets, but you can see that they rely on somewhat arbitrary decisions like random seeds or dropout techniques, and a little bit better algorithms that can allow us more systematically explore that Rashomon set could be needed. So it doesn't maybe give us every single neural net, but a good cover over all possible Rashomon sets of neural networks, where each model then will represent different properties that stakeholder could care about towards the downline. Then how do we display Rashomon sets for human interaction? TimberTrack is a great example, but there are not actually so many interactive tools that we can use and give our domain experts. And imagine if we would have these tools, then we don't need to go through this process that I went with my epilepsy example. I could just give a domain expert, here is your Rashomon set. Please play with it and try to see which one aligns, which model aligns to your expertise a little bit better. And finally, how do we address individual arbitrariness in deployment? It's actually a big problem because it influences our specific lives. Imagine that I was denied in hiring, I was denied in job because of this arbitrariness, because algorithm was not taken care of it properly. That's kind of not a great situation to be in, right? So we truly believe that we should keep building Rashomon set of our pipelines and algorithms, and it will help us to understand better our possible expertise and the need for the domain expertise. Thank you so much for your attention today. We'll be happy to take any questions that you might have left, and please feel free to stay in touch. Yes.
So there was one paper where it showed that the arbitrariness from models that were treated for fairness can be reduced by ensembling. Are there any ways where ensembling might hurt arbitrariness, or is it just in general a good way to reduce arbitrariness in any application domain?
Yes, that's a really great question. The question basically is that we talked about arbitrariness, and it helped, ensembling helped And is ensemble a good technique for that, or can it hurt in some other applications? And I think it's a really nice research question by itself that would be like interesting to explore. I do believe that it can hurt fairness a little bit, because if you give a majority vote, that typically tends to hurt fairness in general. But also it kind of takes away a little bit uniqueness of the models. So if I give that average prediction, I can, maybe there is some model that has some specific properties that I'm looking for, and by averaging, I get that away. But it definitely helps robustness. So that's current trade-off that we are seeing.
It also depends on how you're on some of these models. Like averaging predictions is just one way. You can also like average over the softmax scores or even the logits. So depending on the type of ensemble, it might result in like different ways of reducing arbitrariness.
Yes, so the comment is that using different ways of ensembling may result in different ways of reducing arbitrariness, and it's definitely true. And different methods can lead to different outcomes as well, yes.
And I think there is no free lunch. So if you want a better performance on one metric, you may sacrifice a little bit on the other. So it all depends on like which model you want to use and which metric you care more, and how overall how robust the model is in terms of maybe whatever future situation that will be show up for when after you deploy this model.
Okay, so thank you very much then. Judy and I will hang around for a little bit if you have any other questions. So thank you for coming today and learning a little bit more about the Rashomon effect.